All right, well, we're going to take a look at lesson 1-3 today. So first off, what I'm going to walk you through is reminding you how to get to where we'll submit our answers today. So I clicked on Power School Learning from Clever, Power School Learning. And now from here, go to your pre-calculus class, go to chapter 1, because we're doing lesson 1-3. That means chapter 1, lesson 3. So chapter 1. And inside chapter 1, I'm going to go to the folder that says 1-3. Now there's 4 things required each day. 1, you need to attend class. So being here in person takes care of that option. If you can't do that, remember you can always attend through Zoom so you don't fall behind. But that's number 1. If you are at home and you miss class, maybe you're ill, maybe you're out of town for athletics, whatever the case may be, all the digital resources that you might get from me in class are all going to be linked right here. So you can click those under digital resources. Moving on to number 2, no matter what, you need to take attendance, which I hope you all have already. And now number 3, we're going to go through class. So I would ask you to open up that lesson exam. So for number 3, it says you have to click down below. I don't have any option on where to put this exam. Power School Learning always puts it at the bottom. So this just says click the exam 1-3. Lesson, that stands for bell ringers, and demonstration of learning's link below. That's this link. So go ahead and click that. So we'll be open. And then once that new box opens, hit resume this exam. All right, not resume, start this exam. Just means I've opened it once before. And so that'll take us to number 1, like our bell ringer. So with that, I'm going to get started. Number 1 here. It says to use this graph, the graph of the function of f of x, to determine the domain and range of the function. So that's what we're doing here. We're trying to determine the domain and range. If you need the attendance link, there it is there. So if I want to do domain and range, from a picture, the way I taught you on lesson 1-2 is to use what I call trash compactor technique. You remember me walking through trash compactor technique? Okay, so the graph doesn't get just so messed up. I will first remind you what trash compactor technique resembles. It's like you take out your trash, you have it on the side of the street, and Dallas dump truck comes by and picks it up, throws it in the bed, and then they smash the walls to compress the space. That's the idea. When you want domain, you're taking out the range. You want to smash out the range. And so I want you to envision everything being squashed to the x-axis. And so a way of resembling what our answer is going to be is I'm going to draw down on the bottom here a little line for the domain. It's kind of like a number line. Basically what I'm going to do, this is going to resemble our domain or our x-axis. So these are every x value that's going to be chosen. I'm doing this just so it don't mess up this graph. This point would be smashed straight down to the x-axis. So what I'm going to do is come down here and place that point right here. Now I want you to know this whole curve gets smashed to the x-axis, and this point would get smashed up, so it would be smashed right to there. That would be the x-axis value. What is that? 1, 2, 3, 4. Add 4, and this is 1, 2, 3, -3. All the curve in between would be smashed to the x-axis, and so our domain would simply look like this. We go from -3 to 4 with solid dots. So if you were going to write this in interval notation, would you write it with a bracket or a parenthesis? Brackets. It's brackets. So it'd be -3, 4, smallest to largest, left to right. That's always the way you do that with inequalities. Interval. If we were going to write inequalities, you would say -3 is less than x, which is less than 4. Is that correct or incorrect?
Oh, no.
No, you need the
Line underneath. Solid dot means it's equal to. Said this way, if you have more ink on the dot, more ink, meaning it's filled in. If I use more ink, I need more ink on the symbols. I need lines underneath. I've heard it described that way. Now for the range, what I want you to envision is everything being smashed to the y-axis. So I'm going to change my collapsible walls here of the dump truck. So I want you to envision all of this getting smashed in to the y-axis. So that's the idea. Everything's getting smashed into here. So again, I'm going to do a little number line. This time I'm going to do it on the left side because that's where I got more space. So it wouldn't really matter which side, but for range, it goes up and down. So this is going to resemble my y-axis. This will resemble the y-axis, or the range, I should say. So again, this pot, this dot, we get smashed straight to the y-axis, which is right here. This dot would get smashed to the y-axis here. And the curve as well would all get smashed. So it looks like to me that this curve goes up to here, and then it comes back down all the way to down here, and then it gets smashed back upwards to that point there. So will my range extend from, I'm going the wrong way, I need to go low first, -2. Will it go from -2 to 3? Is that my range? No, it extends beyond it. Okay, so this does not show a point. So will we treat it as a closed dot or an open circle if it's just a solid line? If it's a solid line, you would do a closed circle. Yeah, solid line means closed points, infinitely many closed dots. All right, so let's see, how low is this point down this way? How low do we get? 1, 2, 3, 4, 5, -5. Oh, I didn't say this. If the dot line was dotted, if it was a dotted line, then you would use open circles. This goes as high as 5 units, I believe. So the range would be brackets or parentheses? Brackets. -5, comma 5 with brackets. Or we could say -5 is less than or equal to x, which is less than 5. Would that be right? No, it's not. Someone correct me. What's wrong?
Why?
Why? Because it's the range. That's tricky. Why? WHY, then Y. Yeah, okay. It's range, so that would be the Y. That's how you do it. So over here, we have the range. Here we have our domain. All right, number 2. Number 2 says, use the graph to find the y-intercept and zeros. So let's start with the y-intercept first. Where is the y-intercept at? Okay, the origin right here. And where are the zeros at? Also, oops, I'm gonna write 0. It's also at the origin. So if you were to write the word y-intercept, you would just write the y value. It's assumed when you say that. If you write zeros, it's assumed you're talking about the x-axis. So you would just write a 0. You could also list it as a coordinate point, which would be 0, 0. And another way you could write it is f of 0 equals 0. So all 4 ways of writing this is true. I guess 3 for each. That would be the answer to number 2. And then finally, number 3, use the graph of f of x to test the symmetry. Now, when you look at this, does it have symmetry with regard to the x-axis? That means, does it reflect over the x-axis? No, not x-axis. So we know that's not true. What about the y-axis? Reflects this way? Left and right? No. Okay, now what about the origin? Okay, it seems like it. Well, if it's true, then let me show you something that's always true for origin symmetry. Let's label this point. This point is left 3 units and up 3 units. So I would label this point -3, 3. If something has origin symmetry, then each and every point has its opposite, what I call opposite. It'll have a +3, -3. Let's check this point that it ends at. This one's at 1, 2, 3, 4, down 2. So this point is at 4, -2. Are these points opposite of one another? No, it's not origin symmetry either. So we'd say no symmetry. I know it looks like it's in origin symmetry. What would have to have been true is this point would have had to have been at +3, -3. They would have to be exactly opposite. The way we, by formula, gave this to you last class is we say that f of -x has to equal -f of +x. What that means is that x switches from negative to positive. The y's also switch from negative to positive. That's the formula. And it just means f resembles the y. The y's have to change from negative to positive or positive to negative. The x's have to change from negative to positive or positive to negative. Doesn't matter which way they start, which way they finish, but they have to switch. Any questions over that bell ringer? Okay. So let's get started with lesson 1.3. Lesson 1.3, before I forgot, let's do a little extra practice here, doing domain and range. So a good way of doing domain and range, when you have a picture, that's what I would call trash compactor technique. So let's do this again. I want to clear a little bit more white space to work with here. Let's see if I can get some white space. So let me do that there. And now I'm going to get a number line. So number lines for domain and range. That's going to be my domain number line. And over here will be my number line for range. All right, so if you were going to smash this piece right here to the x-axis, it seems like I would have an arrow that gets smashed down right about at -3 here. So I'd have an arrow. Let me switch colors. Sorry. I'd have an arrow at -3. That's where that is, -3. I have this arrow. I have this open circle. Oh, that's not counting by -3. I didn't realize my scale. That's at 1. Open circle at 1. Sorry, this is not -3. This is -3 here. So what would this be at? This arrow. -3.5. Okay. And all of this solid line would be squished right here to the x-axis. So I would need to have a solid red line there. So from here, going over a solid red line. Now we have a second piece. So you're right. This is piece number 1. Now let's move on to piece number 2. I'll do piece number 2 in blue. It has a solid line or a solid dot at 1. Solid dot at 1. A solid dot at, what is that, 2.5? No, 3. That's 3. So at 3, it has a solid dot. And it's a solid line in between. So let me find blue, solid line. Like that. Okay, now the next, I'll go green. 3. That's not green. Piece 3 here. We would have an open circle followed by a solid line and an arrow out here. So I need a line, green, arrow. Okay, when you look at this domain, does it go forever to the left or does it start at -3.5? Forever. Why do we know it's forever?
Arrow.
The arrow. Okay, so the domain would go forever to the left. Would that need a parenthesis or a bracket? Parenthesis. What symbol represents forever to the left? Negative infinity. This is the domain. Now just do D. Okay, does it break at 1? Does it break at 3? Does it go forever to the right?
Yes.
Yes. So it'd be from negative infinity to positive infinity, or you could say all real numbers with an X. That means domain's all reals. Okay, now let's do the range. So using this first piece, again, it was in red, so I'll do red. It looks like at -4, we have an open circle. Up at the top of the graph, we have an arrow. Line goes down first. So it first goes down to there, and then it comes back up to that arrow. Is that all reals by itself? Answer is no. Why is it not all reals? The very bottom. What about this? Is that open or closed at this stage? It looks open, it's not, because right here could be considered a closed dot, and so it'd fill it in. That's right, but we don't go forever down. So I'm gonna look at the other pieces. Do any of the other pieces go all the way down forever? No, so this piece would get smashed in. It would only be, whoops, wrong color. It would only be at 2. There at a height of 2, it would just be a solid dot. And this piece in green, sure, would have an open circle there. But then it does, if it's range, get smashed over with an arrow. So I'm gonna be a little bit quicker on this one. It would get smashed over with an arrow. So the red fills this one in, fills in the green dot. And yes, we have a line going up, but it's not all reals. It doesn't go down forever. That's -2, that's -3, that's -4. What's that gonna be? -5. So do I need to put, if it doesn't have a dot, do I do a closed dot or open circle? Close. So this one, the range would go as low as -5 in bracket and as high as infinity. The way you would write this is you could say -5 less than or equal to, what letter is range? Y. You would not have to do the infinity. Again, if it's too small for you to see, just open up Zoom and it ought to hopefully make it a little bit easier for you on your computer. Questions over this one? And I made one more quick drawing. I forgot about it a moment ago. I have one more just random drawing. The reason I did this is because I could program graphs. Do y'all remember what the name of this is when it's pieces broken up like that?
Piecewise.
Piecewise, very good. I can draw piecewise and Desmos really well, and it kind of makes us think about it a little bit more. So even though this graph had 3 pieces, the domain was just what looks like one little interval. Okay, even though this was 3 pieces, the range was 1 interval. Okay, so the number of pieces doesn't necessarily change the interval for the domain or range. All right, and now I'll have this one and then we'll move on. So let me get some axes down here. This will be our domain. And I might just go ahead and write range on this one when we get there. Okay, let's do piece number 1 in red. Solid dot at, let's be careful. Each one of these are counting different. This is 5. So what do you think they're counting by? They're counting by 1. So this would be at 2. So at 2, we have a solid dot. Over here at -16, we have this arrow and it's connected the whole way. So there's our domain. Piece number 1. Piece number 2 goes open circle at 2, open circle at 5, connected the whole way in between. From 2 to 5, connected all the way in between. And then finally, this would be at 9. I agree, that's at 9. And so open circle at 9, arrow over here, connected all the way in between. Why does it do that sometimes? Not bad. Okay, let's try this again. Arrow, green. And it goes to the right forever. Okay, is that all reals this time? No. Okay, how far left do we travel? We go from -infinity. Was that parentheses or bracket? Parentheses, -infinity. All the way to, do I break it 2? I have a closed and an open. No, so it stays consistent, it goes across to 5. Parenthesis or bracket on 5? Why parenthesis?
Because not equal to.
Not equal to. So anytime you have a parenthesis, that means it's not equal to it. So we're not actually equal to -infinity. That's not a real number. Union means there's a break. Okay, and the break goes from 5 to 9. Does 9 get a bracket or parenthesis? Parenthesis. 9 to infinity. So the other way of writing this is you would say x is, since it's not equal to, you just say x is less than 5. What's the English word for this union, this u? Or 9 is less than x. You don't have to, you could write the x first, x is greater than 9. You do it that way. But those are the 2 ways of writing the domain there. All right, range. I guess I'll just place it on the actual y-axis here. So we were dealing with the x-axis here, the domain. Now let's deal with the y. And so I have this dot here at, what is that height? 3? Height at 3. Arrow down here, connected the whole way. This is piece number 1. So that's going from -infinity all the way up to 3. Would you agree with that? Do I need to even mess with this piece? The answer is no. Why not? We already know that this piece goes down forever. You actually don't have to mess with it. You can put it on there, but it's actually not necessary. So, whoops. It's not going to make a difference. That's a good way of saying it, because even though it's open there and open there and connected in between, even though you have all of this, the reason it doesn't make difference is the red. What does the red do? The red cuts right through it, goes down forever. So the red would fill that in anyways. So that's why it wasn't necessary to do piece number 2. Okay, what about piece number 3? Open dot, arrow there, and green solid line. Okay, what does that mean about my domain? I mean, my range, I'm sorry. All real. What about this little open circle there that's in blue? Filled in by the red.
Please stop, drop, and submit.
And so we said it's all real, so I'll just do that real quick. Range is from negative, and why is it writing with arrows? Let's try this again. From negative infinity to infinity, or you could say y, e, r. Either one of those would work. All right, so now let's start talking about continuity in behavior and limits. So this is a fun lesson for our future calculus students because you start to get into something where you're predicting where a value is going, whether or not the function's actually there or not. So for example, something you're going to see with limits, so this third word here, limits. What a limit does is it doesn't actually care if the graph exists at a particular point. So you see how on this picture, I know it's kind of hard to see, but if you look closely on mine, do you notice how that's an open circle there? That means the function is actually undefined. Since they call it f of x, I'm going to say f is undefined. Now you'll learn later, you don't have to write f of x. Many calculus teachers will just use the first letter and say f and then name it f. F is undefined at that spot. What that means is it doesn't actually exist there. But when we take a limit, we'll predict what that value should be. So the way they'll write it, notice this L is on which axis? The y. And so this C is on which axis? X-axis. So here's what I'm trying to say. The point C comma L. And if you're like, what the heck is that? Remember, points come as X comma Y. The point C comma L, let's write this out. The point C comma L is undefined. And if you're like, what makes it undefined? It's an open circle. I'll put that in parentheses. Open circle. That means the graph does not actually exist there. It does not exist there. But when we talk about finding the limit, what they're going to write is, well, I'll show you the symbols in a second. The limit, here's how they'll write it. L-I-M. You'll see me do a cursive L every time. That's kind of the normal way. Down underneath the limit, they'll do X approaching. This arrow means as the X values get really close to C.
Teacher, it is my understanding that.
So this is saying the limit, that means you're predicting as X gets close to the C value, the Y, goodness gracious, come on now. The Y, f of X, is approaching what value? As we get closer and closer to C on our graph, what's the Y value approaching? L. And that's how they'll write the limit that exists. So even though the graph actually does not exist, it's not undefined, the limit will. It's kind of like the predicted value, if that makes sense. Now I've got a whole bunch of options I'm going to just kind of walk you through today to show you, but that's kind of your note on that. And I don't know why I'm writing diagonally. That's a good question. I don't know why I'm doing that, and I can't exactly straighten it out. So my bad. Okay. So let's talk about now discontinuity. So you have this word continuity, that means something's continuous. Not everything's continuous. Sometimes it breaks. There are different ways of describing a discontinuity. The first is what we call an infinite discontinuity. That's when the graph at the break takes off for either positive infinity or negative infinity. Notice this graph is broken at C. So the graph, I'm going to call it f of x again because it calls it here. I want you to see that at f of C, the graph is undefined. Undefined. So what does that mean? That means the graph doesn't actually exist there. It's broken apart. And at the break, this value is going up to positive infinity. This one's going down to negative infinity. So the limit, though, would exist. So how you would write the limit is you would say the limit as x approaches, what x value is this approaching? Look on the x-axis. C. The graph itself is approaching positive infinity. So now, even though positive infinity is not a real number, that's where we're predicting the graph's going. Now there's one problem with this, and I'm going to correct it in a second, but I'm going to first do this limit. So for this piece, on this piece, what's the x value approaching? Look on the x-axis. What's it approaching? No, the x value. What x value are we getting close to? C. As we approach C, this value C here, that's a C right there. As we approach C, the graph is going down to negative infinity. Now there's one thing I got to correct. If you have two limits at the same point, you have to state which one's on the left side of the point and which one's on the right side. Since this limit's on the left, you do a C, and in the place of a power, you put a negative. That just means you're on the left side. And on this one, you'd put a plus next where the power would go. And that just means you're on the right side. So what point does not exist? Well, the point that does not exist is C,
All
comma.
right, teachers, I just sent a new link that was sent.
Okay, so what I was saying before the announcement came on, what point does not exist is C, comma, positive infinity. The graph does not exist at C, comma, positive infinity. It does not exist there. Come on, why are you on it right here? C, comma, infinity. That's not a real point. We can't ever get to infinity, but the limit can exist where as it's approaching C, it's going to infinity. The plus just means it's on the right side of C. It's on the right side. And this one, what does not exist is the point C, comma, negative infinity. That's what does not exist, but what can exist is the limit. Okay, jump discontinuity. So all that was to say, this is an infinite discontinuity because the graph was going to infinities. A jump discontinuity is when the graph at the break, so it's broken at C, at the break jumps from one place to another, and it's not infinities. So this one was going to infinities. This one's jumping from a real number to another real number. This is, on this one, that is a jump discontinuity. On this particular problem, f of C, would it be defined or would it be undefined? Very good. How did you know it was defined? There's a closed circle right there. F of X, F of C right here is defined because it's a closed circle. At C, there is a legitimate Y value, whatever that is. Okay, what about on this one? Is F of C defined or undefined? Very good, undefined. And if you're wondering, what am I talking about? You're going to the C value and you're looking at your graph. That's undefined. This would be a removable discontinuity. You just remove one little dot. It looks continuous, but one little dot's gone. By the way, would the limit exist or not exist? Could I write the limit as X approaches C, F of X equals, I don't know, I'll call it L there. Could I do that? The answer is yes. Could you predict what value that is that's missing? Could you look on there and predict? If you could predict it, you can have a limit. So a limit is just a prediction. Doesn't mean the graph actually hits it. It's just the prediction, if you will. Okay, you're going to see a lot of those today. There's just kind of your overview on your notes. Just this is the general overview. Some people like rules, other people like examples. There's your rules page. So let's take a look at some of this. Oh, continuity. Mathematicians love rules. How do you know if something's continuous? Well, the limit has to exist as it goes through here. First off, the graph has to be defined, and the limit has to approach it from both sides. It has to be the same value. That's what's kind of what this is saying here. And not only that, the limit that's approaching is the actual function value itself. So that's, we'll talk about that as we go. I don't want you to stress on that. Okay, so the first one, it says determine whether f of x equals 1 over 2x plus 1 is continuous at x equals half. Justify using the continuity test. So if you were going to prove this, let's first look at the picture. Here's 1/2. Is the graph at that spot continuous at 1/2? Let me mark this right here. At this spot at 1/2, is the graph continuous? You had it right the first time.
Yeah.
Answer is yes. It's continuous at 1/2. I should say f of x is continuous. Let's say f of 1, or I could say f of 1/2 is continuous. Now, how do I know it is? How would you justify it? Here's the proof. Number one, you could say, what is f of 1/2? F of 1/2 equals, if I plug in a 1/2, and let's do a little mental math here. I have 1 over, what's 2 times? 2 times 1/2 is 1, so it's 1 plus 1, and that would equal 1/2. Okay, so we know that f of 1/2 equals 1/2. F of 1/2 equals 1/2. And that's what this point is. That's the x, that's the y. That's the x, that's the y. 1/2, 1/2. And how you could also prove it is then you would say, okay, what is the graph approaching? As we approach 1/2 from the left side and the right side, so that's left side. And this is f of x approaching 1/2 from the right side. You would say, okay, as if I were going to predict what's happening to the graph as I approach it from the left and right, well, as I approach it from the left side, it's getting closer and closer to 1/2. That's the left side. And as I approach it from the right side, it's getting closer and closer to 1/2. Since all three of these match values, it is continuous. Now, that's a long way of proving something that you can see right away, but that's the idea of those proofs. So there are three little things to prove here. That was supposed to be a star, star, and star. Those are the three proofs from right here. Okay, now I'm not going to ask you to justify in the future, but I'm just walking through what that was. Here's your DOL number 1. I want you to graph this and see if it's continuous at 1. Go ahead and graph it and see if it's continuous at 1. If you need something to graph with on your Power School Learning, just click the Desmos and then click a blank graph. So I click the Desmos link. Internet's really slow, and now I'm going to just click blank graph. I'm going to give you about a minute, and then we'll pick up and move on. So you're looking at f of x equals x squared plus 2x minus 3. All right, now let's look at example 2. It says determine whether this function is continuous at x equals 1. So now I'm going to look at this picture, and I'm going to just kind of go through this process a little bit faster than what I did in the last problem, because if I've given you a graph, it's really easy to tell whether it's continuous or not. At positive 1 here, is this graph one piece or is it broken apart into two pieces at 1? Answer is this is discontinuous. F of x is discontinuous. F of x is discontinuous. The reason it's discontinuous is because f of 1 is undefined. How do we know it's undefined? It was broken apart there. What type of break is it if the graph at the break takes off for the infinities? What kind of break would we call this? This is called an infinite discontinuity. This is an infinite discontinuity at x equals 1. That's an infinite discontinuity because the graphs are breaking and going off to infinities. I know this problem is not asking for it, but I'm going to just show you the limits. So on this one, if you were to write the limits, you would have two limits. Why two limits at this break? Because there's two pieces. There's one piece on the left and a piece on the right. So I would have two limits at 1. And so what I'm going to write is x approaching 1 with a minus, and I would have f approaching, an x approaching 1 with a plus after it. So what does the minus and the plus mean?
From the left to the right.
Left side and right side. Okay, on the left side of the break, as we get closer and closer to this green dotted line, as this graph f of x approaches the green dotted line, what's it doing? Going up, down, flat, or stopping? That's kind of the options. Up, down, flat, or stopping. What's this function doing as it gets closer and closer to the dotted line? So here's the options again: up, down, flat, or stopping. It's going down. What symbol represents down? Negative infinity. Okay. So by the way, the way you're tested on this is you'd be given this portion right there, and you'd have to fill in like a blank right here. You'd say, okay, what's the value here? What's the value here? So this is what you'd be given, and you need to understand you're being asked, what's the graph doing on the left side? And you would say, oh, it's going down. So the blank you'd fill in is negative infinity. Okay, this one's saying what is happening to y. Limits are kind of like what is happening to the y when x approaches 1 from the right side. So here's the dotted line at 1. As the graph on the right side, so this is the right piece, as it's approaching this dotted line, what's the graph doing? Is it going up, down, flat, or stopping at a point? It's going up. What symbol represents going up? Positive infinity. So that would be the two limits there. Now you might ask yourself the question, what does it look like when you have something going flat? Well, this piece right here and this piece right here would be those limits. They are really getting really, really flat. And so when it's really, really flat, you would say the y value it's getting flat on, which in this case would be zeros. I won't write those limits down, but I'm just telling you that's what it would look like. These two side pieces, as it goes left forever and right forever, get really, really flat. And that's when that would happen. Okay, let's try this problem. You're looking at x equals 2. At x equals 2. Does it look continuous or discontinuous? What do y'all think? It looks continuous. I'm going to do one test though. I'm going to test f of 2, which means I'm going to plug in 2. I have 2 minus 2 divided by 2 squared. I should put that 2 in parentheses right there. 2 squared minus 4. Let's simplify this math. What is 2 minus 2? 0. What is 2 squared? 4 minus 4. And to simplify it one more time, what's 4 minus 4? Are you allowed to divide by 0? No, this is undefined. I don't care that it's 0 divided by 0. This is undefined. So question, if it's undefined, is it continuous or discontinuous? It's discontinuous. So f of x is discontinuous. Now I'm about to talk about what's wrong with the picture. F of x is discontinuous at x equals 2. Positive 2 this time. Positive 2. So why is it discontinuous when the graph looks continuous? Because it should have an open circle right there. So let's add that in. I'm going to change colors. Let's make it red here. I should have an open circle. And if I wanted to be perfectly precise, I shouldn't have the line going through it. So let me try to color over the line. There we go. That makes it a little bit better. That's an open circle there. Now, how do we do it? Figure out it was an open circle. When I plugged in the 2, I got division by 0, and you're not allowed to do that. So f of x is discontinuous. What type of discontinuity is at 2? Was this infinite right here, jump, or removable? Look at your little cheat sheet. Go back and look at your cheat sheet. Is this infinite, jump, or removable? This is removable. So we have a removable discontinuity. We have a removable discontinuity at x equals 2. All right, why is it removable? Let me show you the algebra. Here's the algebra. If you're wondering why is it removable, if you performed a little factoring, you might remember this from the first day of class, the X method. I told you that there is a shortcut you can do if you're missing your B term. It's called the difference of squares, or I call it sometimes square root technique. You can factor this. If you don't remember how it factors, anytime you're missing your B term, you can take the square root of the first term. What's the square root of x squared? It would be x in x. And then you take the square root of the back term. What's the square root of 4? 2. And so you have 2 and 2. You make one positive and one negative. That's the algebra. That is f of x. That's how it factors. What could I do with these factors? Are you allowed to cancel factors? Answer yes. What do you notice about my factors here? X minus 2. They can cancel or simplify, which means this could be simplified to be 1 over x plus 2. This right there is the removable discontinuity. If you're going, why is it x equals 2 when it says x minus 2? Because to get 0 here, you're not allowed to divide by 0. On this particular value that does get simplified or removed, x would have to equal 2 to make it 0 in the parentheses, because it's 2 minus 2. You see how 2 minus 2 would give me 0? And that's why it's a positive 2 there. And we call it a removable because it got removed out of there. Now, what would you call, so this one right here, that's a removable discontinuity. That's removable. What would you call this one over on the left? We never even talked about this one. What would I call that removable? I just call it removable. That discontinuity. It's not removable. That is a infinite discontinuity. So let's go ahead and just write that in so we know it. It's an infinite discontinuity. Infinite discontinuity at x equals, what is that? -2?
Yeah.
At x equals -2. And that comes from this one right here in the algebra. That was the removable. It got removed. That's the removable. Truthfully, I should be pointing at the denominator. That's the removable. This one that remains is the infinite. And again, it would be -2 that would make this be 0 because it remained forever. So that's where they came from algebraically. I guess I could have pointed at that one right there. Make this a little bit cleaner. It's infinite because it remains forever. That's where that comes from. Okay. So I'm giving you a lot of information. I understand that. But I want to just be a little bit more thorough. Okay, I want you to graph this and see if it's continuous. By the way, Desmos can help us by, if you ever want to open the table, you hit settings and hit the convert to table. And if it has a break, let me show you the previous problem. If it is discontinuous, let me show you what the table will say. This problem was x minus 2 over x squared. Gosh, why is it doing this? -4. Okay, what I want you to see here is it'll say undefined anywhere it has a break. So this one, it doesn't show an open circle unless I like highlight it perfectly. Then it would show me an open circle there. As you can see on my Zoom or on my Desmos, it has an open circle at 2, but it doesn't show it unless you click it perfectly. And so those two values you can see from the table are undefined. It's undefined at -2 and it's undefined at +2 as well. So that is a way of using, you can use your table. Again, you just go settings and then click that convert to table, and you can check that way to see if it's undefined or not. So now here's your DOL. All right, now let's talk about the intermediate value theorem. This is very basic, but it's got powerful implications. What the intermediate value theorem says is this: if you have a graph that's continuous, if it's continuous and you have a point on the x-axis, let's call it A, and another one B. So you have f of A and f of B. If this graph is continuous and it, let's say A is increasing to become B, then there's going to be a point C that could be found in the middle. That's all this is saying, is that if it's continuous and you have a point on the left, a point on the right, you could find something in between the two because it's continuous. If it's not continuous, then obviously there could be a gap. But if it's continuous and you have a point on the left and a point on the right, guess what you can find? Something in the middle. You can find something in the middle. Okay. So now it says determine between which consecutive integers the real zeros are located on the interval. So this time we're not actually going to be locating the exact zeros. Now, what was the definition from last class of a zero? What's a zero again?
It's the x.
X-intercepts. Yeah. We're not actually finding the x-intercepts. That's not what I'm wanting to find on this problem. So I'm not looking for what's this x-intercept, what's this intercept. What it's saying is, let's find the two values that it's in between. So what is the integer value? So not decimals. What's the integer x value that's to the left of this point? The first integer to the left. So you're looking at your x-axis. What's the first integer? Just means whole number, positive or negative. Zeros to the right, we will use that one, -1. What this is saying is the 0 will the 0 will fall between the 0 occurs between -1 and 0. I'm just going to do parentheses because I know it's not at -1 and it's not at 0. It's in between. So I'll just do parentheses. I know that the 0 occurs between those two spots. Now there's a second 0. So what two integers does that fall between?
1, 2.
1 and 2. So the 0 occurs. I'm now going to make it zeros occur. Let me change my between there and the other one would be between 1 and 2. Does that make sense what I was writing there? This is just following up on the intermediate value theorem. It's saying, hey, if we know that there's a 0 here and this is a continuous line, we can find a point on the left and a point on the right that would surround those two. So we're just saying we have some 0 in here. I can find a point to the left and a point to the right around it. And that's what we were doing there. Okay. Let's try this one. Determine between which consecutive integers the real zeros of this equation occurs on the graph. Okay, this one, how many zeros do you see? 1. And it looks like it occurs between -1 and -2. So 0, and it's just 1 0. So 0 occurs between -2 and -1. Now I'm using parentheses. Why am I using parentheses? Does this 0 actually occur on -2?
No.
Does it actually occur on -1? No, because I know it's in between, I'm just going to use parentheses. All right. Your turn. And it looks like they switched to inequalities. I want you to graph this and see where you think zeros occur. I'll give you a couple minutes here. So there was part A. Now part B, I just graphed part B, and I'll let you make up your choice on part B here. Let me zoom in a little bit. And I guess on Desmos, you could click it to help you figure out between what integers this would be located. On part B here, the correct answer is 5, 4, 3, 2, 1. Which on, this is part B now. What would be the correct answer here? B, be between -1 and 0. It would be between -1 and 0 for part B. All right, I'm now going to look at example 4. So now let's talk about end behavior. So I've talked about limits as a graph was broken apart in the center. Now I want to talk about what's called end behavior. Whenever you see end behavior, it's talking about two specific limits. What it'll be talking about 90% of the time, maybe even more than that, is the limit as x approaches -infinity and the limit as x approaches +infinity. Said another way, it's talking about on your domain as you go off this either side, what's happening to your range. So all you're paying attention to when you see end behavior is what is the graph doing as you go off the page to the left and off the page to the right. Is it going up, down, flat, or stopping at some point? And again, how you get this on a test is you'd be given these symbols and you'd have to fill in the blank with what the correct answer is. Okay, so let's figure this out together. On this graph, as I go off the graph to the left, so that's what end behavior is talking about. How does the graph end to the left and to the right? As I go off the graph moving left, what is this graph doing? Going up, down, left, or right? Answer is it's going down. What symbol represents down? -infinity. That means ultimately this point is approaching, I know it's not a real value, but it's approaching -infinity, -infinity. That means it's moving leftward and downward forever. That's what it's approaching. So I should say approaching because it never actually gets there, but a limit predicts where it's heading. Okay, what about as we move right forever? Is this piece over here going up, down, flat, or stopping at some point? It's going up. What symbol represents up? A positive infinity. So that would be my answer for that limit. Again, if you were going to write it out using words, you'd say it's approaching. What point is it approaching? It's approaching the point positive infinity, comma, positive infinity. That means it's moving right and up forever. Okay, now I'm going to give you one to try. So basically, just so you're clear, on the test, you'd be filling in this blank. If you were taking your digital test, you'd be filling in these. I know this is multiple choice, but that's the part you'd be typing in. Everything else would be given to you. Notice this is the limit as the graph moves left. This is the graph moving left. Graph moving left. This column represents the graph moving to the right. Okay, so that'll help you out finding the correct solution here. I want you to figure out what's happening as this graph moves left, what's happening as it moves to the right. Example 5, it says use this graph to describe the end behavior of the equation f of x. Support the conjecture numerically, and I'm actually going to support it through Desmos. I'm going to show you, it's kind of the easier way. And I'll tell you how you can do it algebraically, but I'll show you. So on this graph, what we're trying to find is the end behavior. Again, when it says end behavior, it's talking about the limits as the graph extends off to the left and right forever and forever and forever. And so the way you would write this is you would have limit f of x equals, we got to figure out the y. As x approaches the left, that would be negative infinity. Or we got our also, I should say, also, we have to find the limit as x approaches positive infinity, meaning as the graph moves right forever. Now, there's 4 options to any graph. The graph will either move forever to the left going up, move forever to the left going down, move forever to the left.
Sorry, teachers, one last interruption.
All right, as I was saying, the graph can either move up forever as it moves left, it can go down forever as it moves left, it can get flat forever, or it can just stop at a point and not go forever to the left. Those are the only 4 options. It's either going to move up, down, left, or flat, or just stop. Okay, on this particular problem, it's a little tricky to see here. And so I'm going to move over to Desmos to help me out. So I'm going to graph this equation because we can manipulate Desmos by zooming in and out. And that's what I'm going to do here. And I'm also going to use the table to support our answer. So as I move out, now the graph becomes easier to tell me the true answer. As we go left forever, what's happening to my graph? Is it moving up, down, flat, or coming to a point? It's getting really, really flat. And so if it's getting really, really flat, you got to determine what number is it getting flat on. And the way to do that is to go to table and then start picking numbers that are way to the left. So for example, I could do -10, I could do -100, I could do -1000. I can just keep going left. And this number is getting closer and closer to, y'all know what's getting closer to?
0.
Getting closer and closer to 0. Very good. Because what was happening, if you watch, each time it was getting a little bit smaller. That's it's like -7 pennies. Here, it's like not even -1 penny. Like that. And so this just means move the decimal 4 times over. This means move it 5 times over, 6 times over. It's basically getting to 0. This graph, as you move left forever, approaches 0. The y value is 0. It's getting flat on 0. Typically, if it's getting flat on a number, it'll get flat on the same number going the other way. Let's check it. So right now there's a 2. Here I'll do a 10. You see how it's 0.13? I'm going to change this to 100. Now it's 0.01. 0.001. What does it seem to getting closer and closer to? 0. It's approaching 0 as well. And like I said, 90% of the time that will be the case, is that as you move left and right, again, this is the fill in the blank portion. If you were tested, that's what you got to fill in. 90% of the time, probably more than that, If it's getting flat, it's going to get flat in the number both ways. This is what we'll learn. It's called a horizontal asymptote. What's a little bit different than horizontal asymptotes from the infinite discontinuities is infinite discontinuities, the graph will never cross, like they're broken there. A horizontal asymptote in pre-cal, we may cross over, just like this problem, it crosses over the horizontal asymptote. That'll happen frequently in pre-cal, but it just means it's approaching that value. It's going to get closer and closer to that green dotted line on both sides. So that would be the answer there. It gets flat on 0. And so those would be the limits. If we have time, we might come back and fill out the other limits around. So this limit, I want to make sure you're aware of this. This limit is representing that arrow right there. That's where the graph's going. This limit right here is representing this arrow right over here. As it goes right, it goes down forever. So those would be those two limits for this problem. Okay. I'm going to give you one. So again, the limit here on the left side, this is the left end behavior. The left end behavior is corresponding to this arrow right here, left end behavior. This limit is the right end behavior. I'm just going to say right end or ED, and that's not how you spell behavior. NEB. There you go. Right end behavior. This arrow is talking about the right end behavior. So that's what you're looking for, or where you're looking. The questions you ask yourself, is it going up forever, down forever, flat forever, or is it arriving at a point? Let's take a look at example 6. Real world, let's apply this. It says the symmetric energy function is E equals all that. If the Y value is held constant. Okay, question for you. Y value is held constant. What does that mean? If it's constant, it stays the same. So basically you can substitute a number in there. What happens to the value of the symmetric energy when the X value approaches negative infinity? And so basically what's happening, since I haven't shown you the algebra of this, is we will graph this and we'll just put in a constant or ignore that for a second. How you would do this algebraically is you'd ask yourself, what happens to E if X is approaching, here it says X value, this right here, X value approaches negative infinity. What all that means is X is approaching negative infinity. So I'm going to just substitute in negative infinity for a second, square it, plus Y squared divided by 2. And so here's the math. I know you can't actually work with the negative infinity, but here's the idea. This is approximately, what is a negative times a negative when you square this? Positive. And infinity times infinity is still going to be infinity. So you have infinity plus some value of Y that's not changing, divided by 2. So here's the idea in math, the math concept. If this is constant, infinity is so large, even if Y is like 1,000, what's infinity minus 1,000? Still infinity. That's still the idea. It's going to be infinity divided by 2. And now what's infinity divided by 2? It's still infinity. So the idea here is that the limit, without graphing it, as X approaches negative infinity, the graph is going to approach positive infinity. I'll say that again. This little part here that we just filled in, that's that answer right there. What we're going to determine when we graph this is we're going to see this graph as you go left forever is going to go up forever. So I'm going to type in this equation. So here's the equation. E equals parentheses X squared plus Y squared over 2. And it's going to say it's not working. Well, if you plug in a number here for Y, because it said it's held constant. So for a second, I'll just plug in a 0. We get a graph. Okay, you see the graph? What's happening as we move left, as X approaches negative infinity? What's happening to the graph as we move left? Which out of the four options, is it moving up, down, left, flat, or coming to a point? It's going up. Okay, but someone says, what if y is not 0? Well, let's try a different number. Someone throw out another number. 4. What if it's 4? What happens as we move left? It still goes up. Okay, someone throw out a different number. 9. What happens as we go left? Still go up. What if someone said, let's check that. Let's make it a negative number. So let's make y be a negative number. What if it was -9? Well, what happens as we go left? Still goes up. So you see how it doesn't, y doesn't even matter? Because anything that infinity, it's just not going to affect infinity. And so for that reason, that would be our limit right there. So people will make predictions using limits all the time. This is just saying, okay, if I hold my y constant and we're looking on the left side, it's going to go to infinity. That's the idea of a limit, is making predictions. Okay, your turn. You have a different equation. And it gives you a value here. It says the intensity is 130. That's your hint. I'm telling you, it says the intensity is 130. I'll let you figure out what that means, but I got it underlined. I want you to figure out what the correct answer is this time. All right, let's take a look at the ACP questions. How might this lesson be tested? This lesson is most often tested off of discontinuities. It's a very easy way to make a test and to not be confusing. And so most frequently you would see the test based off of discontinuity. So here's a problem. It says, given this function, which statement describes the discontinuities? And I love these problems because if you know the vocabulary, it's really easy to figure out your Desmos, because all you have to do is graph them and look at the particular options they give you. So let's graph this problem. This says f of x equals, and I'm going to zoom back in here. F of x equals, it's x squared minus 9 over x minus 3. And when you look at it on first glance, does it look like it has any discontinuities? So what would you guess right now the answer is going to be? F. I would guess F, but we should investigate. And here's why I say I love these problems, because they tell you where to investigate. Where should we investigate at? 3. The easiest way to investigate is to hit edit list and hit convert to table and type in the number 3. What happens at 3? So does that mean it's continuous or is it discontinuous? Discontinuous. So now we know F is not true. And so you ask yourself the question, okay, what type of break is there at 3? Does this graph at 3 jump or have, infinite jump, or would it be removable? And I will click it at 3. Here's 3. What type of break is it if it's just one little open circle along the way? Removable. This is a removable. And so algebraically, what that means is if I factored this using difference of squares / square root technique, if I factored this, what we would get if you take the square root of x squared, you get x, and so that would go in both parentheses, x and x. If you take the square root of 9, you get 3 and 3. One's positive, one's negative, and I have x minus 3. Remember, you're never allowed to divide by 0. So right now, I could say quite confidently, if you remember from domain, x minus 3 cannot equal 0. So I know x cannot equal 3 in the actual function. So it's going to be broken. That's why. But when I look at the actual problem, after I factored, I can now say, these factors cancel or simplify, or what's the other name that means cancel factor? Excuse me, cancel, simplify, remove. I can remove those. And that's why it's called a removable. It's because I removed it. Okay, there's that problem. And we got one more here. Pauly's given this function. I gave you this on X method day. I don't know if you remember this. I gave you this DOL on the X method day, and I said, hey, I know you don't know the vocabulary, but this is how we use X method. So this problem is incorporating what we learned today and X method day. This time I'd have to factor the denominator. So I'm going to factor this real quick. Do we have any greatest common factors here between x squared, x, and -6? No GCF. So out of our 4 steps, we have no GCF for the denominator. I'm factoring the denominator is what I'm doing here. Step 2, I would do X method. Here's my A, here's my B, here's my C. What's my A if there's no number? 1. So it's factors of, this is A times C, this is B, this is M and N. So I'm looking for factors of -6 that add up to 1. What are factors of -6 that add up to 1? Some of you might know it off the top of your head. Is it 1 and 6 or 2 and 3?
It's 2.
2 and 3. How do I get 1 out of 2 and 3?
Just make one of them negative.
Yeah, which one needs to be negative?
The 2.
The 2. So it's 3 minus 2. Step 3, you'd split your A power, which in this case is just an X. I mean, a squared, so it becomes an X next. And then I put the +3 and the -2. And so step 4, there's no bottoms up on this problem. There's nothing that can reduce. No bottoms up, no simplifying. So what does that mean? I could refactor this as X plus 3 over X plus 3 times X minus 2 plus 4. I'm showing you the algebra way of solving this problem. It's probably the slower way. Look in here, this X plus 3, what happens with those? That's a removable discontinuity. You should have a removable at -3. Because again, the problem is when X is, when we have 0 here. So removable at -3. So the answer has to be A. This is an infinite because it remains forever. That would be an infinite. If you graphed it, you would see the graph confirms exactly what I just did. X plus 3 over X squared